So let's get a fourth video here about relative error of differentials. See, if you thought that, you had some x value, in which case you would have computed some f of x value, but maybe your x value was off by some little bit delta x. So you might have been anywhere in this range right here for your x values, right? Then obviously your function is, between here and here, but, it might change more up here than down here, or vice versa. So we can approximate that error by sticking a tangent line, as we talked about a bunch now, and the tangent line changes by dy here, and if I moved back a delta x, then the tangent line would have changed by that same amount dy down here. So in other words, if x is between x minus delta x and x plus delta x, f of x is between f of x minus delta x and f of x plus delta x, but it's approximately between f of x minus dy and f of x plus dy, right? F of x plus dy, f of x minus dy, right, is how much the, your approximate error in your calculation is. So for instance, if, so what we want to realize then is we've got an exact relative error. And this is the fraction made by your true error, which we've already said is delta y, over the amount. Well, the amount that you predicted was y. So we approximate delta y with dy. So your approximate relative error is going to look like dy over y. So suppose that your function y is volume of a sphere, and of course that's going to leave you now with your f prime being, the 3 is going to come down to cancel, and this is going to be 4 pi x squared. Well, remember that says dy dx is 4 pi x squared. Multiply both sides by dx, and dy is 4 pi x squared dx. So you've got your y and you've got your dy. We want to take dy over y to get the approximate relative error. So when I take dy over y, I'm looking at dy, which is 4 pi x squared dx, over y, which is 4/3 pi x cubed. The 4's cancel, the pi's cancel. These x's cancel, leaving an x down here. See the dx over x? And this 3, like downstairs, really just comes up upstairs. This is 3 dx over x. So then your approximate relative error in your output is 3 times the relative error. That's not approximate because remember dx equals delta x all the time. So this is 3 times your relative error in your input, right? So for instance, if you thought the radius was 20 and there's like a give or take of 0.1 in your calculation, then maybe the radius is between 20.1 and 19.9, in which case now, your function is gonna, your computed volume has a range that it's going to be off as well. Well, that range that it's off is approximately, because we're using dy to substitute for delta y, is approximately 3 times the relative error in input. In other words, look at this relative error input. This is dx, which is 0.1, over x, which is 20. You're taking 3 times that. Well, what is 0.1 over 20? It's 0.005. This is 3 times 0.005. So see how this is half. This is half a percent, right? Your relative error in input, which is half a percent, because you're talking about 0.1/20ths is your relative error in input. That gives you your relative error in output, which is 3 times that, which is 0.015. That's 1.5%. Whoops. That's 1.5%. So your relative error of 0.5% in input is going to yield, an approximate, because we're approximating delta y with dy, an approximate relative error in output of 1.5%. So that's how relative error works. We approximate relative error with dy over y. Just cook it all together, and then you can talk about, your relative error in output being some multiple of your relative error of input, right?